Hello everyone, welcome. This is CIS125, Discrete Mathematics, and this is Bob. You should know me by now, so welcome to class. This is what we're going to do today. Today is really kind of our first real lecture, if you want to call it a lecture, on the subject matter that we call discrete mathematics. So really kind of what I want to do today is kind of set the tone for how we're going to be approaching this course. So I'm going to kind of go into it and kind of like give you some tips on, how you should be listening and how you should be applying the things that I'm going to be covering. So anyway, the main objective that I have today here is I want to put you guys at ease a little bit about math in general. And that's my main objective. Now, to do that, we're going to talk about a few things. We're going to talk about what is discrete mathematics, what we use it for. We're going to talk about different kinds of numbers. We are going to talk about different ways that we could use these numbers and how we could take, simple operations in math, such as multiplication, division, and do complex things with it. But pretty much, this is kind of going to be all over the place as far as lectures go, because I want you to kind of approach this class and I want you to think about math a little bit differently. So let's get started. Now, just about all of you that are here in this class I'm not going to say are here against your will. Very few people enjoy math, right? You're probably in the majority if you're one of the people that are raising your hands right now and saying, Bob, math sucks, I hate it, and I'm here because I need to take it, because I need this for my computer science transfer, or I need to take it for part of my degree, or it's some, part of a required class, like where it says like pick one of the three, and this one just so happened to be available this semester. So one of my objectives to you guys during this semester is I want to try to change that. I want you guys, how about this? In a perfect scenario, I want you guys to like math. All right, I can see you guys rolling your eyes from here. Okay, you're not going to like math, but what I can do is I can at least try to erase your fear of it and try to explain, as we go, how math works without just throwing a bunch of X's and Y's at you and giving you equations. Basically, in my opinion, again, this is my opinion, is, math was never meant to be fun for us. Math stopped being fun for us probably when we were in elementary school sometime. When we were in elementary school, we learned math, by doing fun things. We have word problems. And when we were in first grade, we learned addition, about if you have a monkey and a monkey has 2 bananas, and then you give him 2 more bananas, how many bananas does the monkey have? Well, the monkey has 4 of them. Well, that's kind of a fun word problem, and it's kind of like a story, but that's how we started to learn math. But somewhere between there and here is being where we are today, that concept got lost. And you can go into a lot of reasons why that happened. A lot of it has to do with education. And in education, and somewhere along the way, we started paring down how we teach things to people, and started concentrating on what we teach. And that sounds kind of strange, but if you think about it, when you had math as an elementary school student, you were probably taught in a specific way to learn something. And then along the way, it's like, well, we can't spend time on how to teach someone how math works. So we're just going to concentrate on what to teach them. It's kind of like one of my favorite movies. It's called Mr. Holland's Opus. If you haven't seen any good movies, go on Netflix and rent it, or get it for free. It might be free on YouTube Red too. Mr. Holland's Opus. It's about a teacher that, he was a music teacher, and they were making budget cuts, and they said, we're going to cut music, we're going to cut all these other things, and then one of the reasons is we need to concentrate on reading, writing, and arithmetic. Reading and writing, reading and writing, and reading and writing. And some of the teachers stood up and said, well, pretty soon we're not going to give these students anything to read and write about. And that's so true. And I'm getting a little bit sidetracked here, but that has a lot to do with, I think, of our fear of math, why we don't like it, why we look at it, because we've been indoctrinated with it. Think about it. Ever since middle school, you have been given math without any context, even algebra. I mean, algebra, which I actually think is probably one of the hardest maths to learn. And, we do that in 8th grade and freshman year. And I could say, over a different argument sometime as we can have that discussion, I think that's the hardest math you'll ever do. Because after that, it gets easier. I think it does. But we start learning math in the rote method. For example, and you guys know the rote method anyway, because when you guys were learning times tables when you were in 2nd or 3rd grade, you just would learn it rote, which means that 8 times 6 equals 48. Why? Because 8 times 6 equals 48, right? You know what I'm talking about. 9 times 9 equals 81. Why does 9 times 9 equal 81? Because we said so. Now, you could break it down, right? You could just go 9 times 9 is 9 plus 9, 9 times. And I'm sure you had a teacher explain that to you. But how were you evaluated on that? You were evaluated on how fast you get those timetables done, weren't you? Right? You were. You were given your times tables, your 2s, your 3s, your 4s, your 5s, and you were timed on it. And when little Billy or little Wilhelmina didn't get their times tables done in a certain point of time, all of a sudden there was a problem. And then your teacher had to intervene, and you had an IEP, and then your parents come there and they're like, why isn't little Billy or little Wilhelmina learning their math? Well, little Billy and little Wilhelmina aren't learning their math because they're not being taught correctly. Now, that's not an indictment of your teachers, because your teachers work hard and they do the best they can. But with the resources that were available to them, they were really graded, and your school was graded on how fast you learn things. They weren't graded on how you learn them. They weren't graded on you understanding how this stuff works. It's just, if little Billy gets his timetables done in 2 minutes, we're good, and then we're going to pass you on to the next grade. And then it kind of kept compounding itself. Then you started learning pre-algebra. Then you started learning algebra. And somewhere along the line, right in there, everything lost its, I would say, fun, but you could probably debate and say, Bob, none of this is really fun. But it lost its context. You would just say, you would be given an equation, and n would be x equals 3 over y squared. Okay, great. What does that mean? And then you just would go through the steps. Well, that's what our teacher showed us. We do this, then we do this, then we do this. Then we did the other thing, and then we get our answer. Okay, your answer was right or wrong. If it was right, you didn't know why it was right? You probably didn't, be honest. Okay, sure. But if it was wrong, again, there was a problem. So you were really graded, and your school was actually graded on what you didn't know. And they were graded on what you knew without any context of why you knew something and the things that you didn't learn. That's probably a better way for me to put that. So one thing I do in this class, I try to break that. I try to reimagine. I know we overuse that term nowadays. I'm going to try to reimagine how we think of math, how we think of numbers, and how we can apply this stuff. So when you get out of this class 16 weeks from now, I want you to feel not just that this was a good class that Bob gave, and hopefully you will. Not everyone will, but I'll try, and we'll see how that works. But I want you to at least have a renewed understanding of why we do things, what numbering systems mean, how we apply them, and what it all means, and why it's important to you. I mean, because I'm guessing that most of you think math is important to you because you've been told so, rather than you saying math is important. I want to try to turn it around. That's going to be tough for me to do. It really is, because I could teach you math fairly simply, but I can't teach you to change your attitude. You can teach yourself how to do that, and I'm just going to kind of give you the tools to do it. So as you can notice now, what I'm doing is I'm giving you this lecture, and I have no overhead. and I have no video. If you could look at the video, I just have the Triton crawl going across. You're not having technical problems. I want you to just to listen to this. I don't want you taking notes. If you need to take notes, you can. I don't want you hyper focused, paying attention to the screen, and me showing you all these genius math things that I know that I try to impress people with, but at the end of the day, millions of other people know it too. So I don't do that. I want you just to listen to how we're gonna approach this, and basically what we're gonna do to get started here. So anyway, so that's my first point. My first point is what I kind of want you to look at math and how I want you to kind of treat math and numbering systems. So let's talk about math in general, and then we'll talk about discrete math, and then we'll talk about the different kinds of numbers. But let's talk about math in general. We use math quite simply to describe the world around us. Now, I got some really good news for you. Okay, the really good news is you as human beings, and hopefully you're all human beings, right? If you understand this, at least you understand English, and you're a human being, unless your dog's listening. And sometimes I think my dog is more intelligent than me anyway. But when we were early in our development, let's go back a long, long time ago, like way, way, way back, like before the 70s, okay? We were wired for math. When we were, trying to figure out as a new species, we would observe things, like it would be cold, then it would be warm, then it would be cold, then it would be warm. And then we would start putting patterns together. We would start putting patterns together like that we notice that it gets bright out once in a while, then it gets dark, it gets bright, and it gets dark, and I'm being vague on purpose. So eventually we would start counting things. We would say, okay, well, we noticed that when it gets cold, we have 100, I'm using rough numbers here, we have 180 different occurrences of it getting bright and dark, and then it gets cold again, then 180 occurrences, and then it gets warm again. So we're starting to count things. So we're born to do this. It's in our genes to actually do math, to actually count things. So we would start putting together simple calendars. And from there, we would count other things. When we would go out hunting and gathering, we would note how long it would take to go to a hunting ground or to go gather fruits and vegetables. We would measure it by how many times the sun came up. When we were exploring, we would note how many ships that we would need to carry a certain amount of people. If we had 50 explorers and we knew each boat handled 10 people, we would know how many boats we would use to do that. So when we talk about math, we talk about something that we already know. I was reading an article just recently about trigonometry. And if you don't know what trigonometry is, look it up, okay? That's a different class. But for those of you that, we'll just go on. You know what trig is, right? So, and the article was about how they found that the Greeks, right? They get the credit for everything, right? They invented calculus, democracy, and the chronomatic, right? But the article was the Greeks invented trigonometry 2,000 years before initially thought. And I was reading that, I'm like, wait a second, the Greeks didn't invent trigonometry. No one invented it. Trigonometry was already here. Trigonometry, it already existed, and then we started understanding it. So that's the one thing about math that I want you to take away is we don't learn math. We already know math. And when we discover new ways to use it, we take our mathematical mind and we advance it. Just like when we talk to somebody and we play, here's a good one. Like if you play a musical instrument, when you practice it, you get better. But that doesn't mean you discovered music. Music was already there. And you already had some sort of innate ability to play it. But the more you practice it, the better you got at it. You didn't discover music. You're just getting better at it. The same thing goes with math. You don't learn it. You already have it. You just get better at using it. So to go into this trig thing, so the article was talking about the Greeks inventing trig. And I was like, the Greeks didn't invent trigonometry. If they did, they understood it. But certainly, and I'm not going to get in a debate like who learned it the fastest. I'm just trying to give you an example of math is all around us and we just understand it, right? Like, for example, the Polynesians, when they went from island to island, on little boats in the Pacific Ocean, they were able to figure out from thousands of miles away, literally looking for needles in haystacks for islands. When they were going from Samoa to Guam to the Marianas to Hawaii, they knew where they were going because they would look at the stars and they would use trigonometry to figure out how to get there. Did they use the term trigonometry? No. Did they write a lot of this down? No. But they understood it. They didn't invent it. You see what I'm saying? That's an important distinction. They understood that if they would look at the stars and look at the position of the stars and note that when they would paddle for a day, they would look at the stars and notice they would be in a slightly different spot. Then they would paddle for another day, and they would notice that the stars are in a slightly different spot. And they would look and they say, that's not a coincidence. We know that when we move our boat, these stars are in different positions. And when we get to that land with the volcano and the hula girls and the tropical drinks, okay, they didn't have that back then. Well, maybe they did. Maybe that's why they went to Hawaii, right? So they would notice, they'd say that then when we got to that land with all the volcanoes, we would notice that we were gone for 8 days or whatever, and the stars were in a certain spot. That's trigonometry. And they wouldn't say that's trig. They wouldn't write it down. The Mayans did that when they did a calendar. The Mayans actually, not as a coincidence, invented zero, which we're going to talk about at a different time. The Egyptians used trigonometry. The Greeks used it. Everyone used it. So what I'm trying to say is math is inside of you. Math is something that you already know that you just need to get out. So how does that apply to what we do in discrete math? Now, what discrete math is discrete math is a set of mathematics that we use that deals basically with whole numbers. And let me describe this a little bit. I'm going to kind of circle around a little bit. All right, let's talk about simple numerical. Let's talk about simple numerical systems here. We're going to talk about real numbers and we're going to talk about whole numbers. Specifically, we're going to talk about integrals and real numbers. Now, integrals are discrete numbers or are numbers without fractions. For example, and let's talk about, again, describing the world around us. If you look around you right now, and I just want you to take a look around and look at things that you can specifically count. If you're I live in the city, so I take the CTA. So if I'm on the red line, I can look around me and I could count the number of people that are on my car. I can look in my backpack and count the number of things that are in there. I can look out the window. I can count the number of buildings I see if the train wasn't moving, and I could look and I had time to count all of them. Now, what I'm talking about there is I'm talking about what's called an integral or a whole number or an integral number. Integral numbers and whole numbers don't have fractions. For example, for the most part, when I'm looking around on my CTA train, I don't see 20 and a half people. I see 20 people. If I look to see how many items I have in my backpack, I got 8 items. I don't have 8.5 items. I have 8 items. When I look around and I count the buildings outside the window, I count, if possible, 75 or whatever. I don't see 75 and a half. Now, let's get over the fact that maybe a building's under construction, but let's just go with the fact that a building is either there or it's not there. Okay, so we're dealing with whole numbers here. Now, that's actually an important concept because when we deal with that sort of observations, we're dealing with what are called whole numbers. We don't see 18 and a half people on the CTA train. We don't see 14 and a half things in my backpack. And we don't see 75 and a half different buildings. We see whole numbers. Now, that's important because when we talk about a whole number or something that does not have a decimal in it, we talk about discrete numbers. And that's where discrete math comes. Now, I don't want you to get really, really super hung up on the definition of discrete math because it's kind of a collaboration. Discrete math kind of describes the kind of math that we use for things like computer science and other sort of sciences. It's not like calculus or algebra or trig that was either invented by a certain mathematician or describes a specific set of math. Because you can look at geometry, right? And you could say, just tell me in regular plain English, you could tell me how geometry is different than algebra or how calculus is different than trig because they're different sorts of math that you do, right? Discrete math is not like that. It's kind of almost like math by committee. The term, I believe, I might be wrong on this. I know that, I might get corrected, but it's only about 40 years old. I think it's like the 80s or the 70s where the term kind of came up to describe the study of discrete quantities or whole numbers. That's basically discrete math. Now, we're not going to really get into that too much as far as the definition goes because this isn't, the class on definitions. But for those of you that asked kind of a little bit about discrete math, it really is, in my opinion, a kind of a vague term, which is fine. It just basically talks about the math that we use for specific sciences, specifically computer science, and we kind of lump that into discrete mathematics. Now, we talked about whole numbers. Whole numbers are integers, right? Integers are whole numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, right? Or whatever. And I'm kind of being vague on purpose. Now, we also have a lot of numbers between those numbers, right? Think about it. So if I'm looking at, how about this? How many numbers, and we'll put your virtual hands up here. How many numbers are between 9 and 10, right? And you know what? I'll make it we'll keep it that way. How many numbers are between 9 and 10? A lot of you are scratching your head because the mathematician in you is having a hard time answering that because you say 9 is a number and you say 10 is a number. So your professor just asks you how many numbers are between them. You might say none, right? But think about it. Keep going. None. There are no whole numbers between 9 and 10, right? So that's correct. There's no whole numbers between 9 and 10. You have 9 and you have 10. But are there quantities between 9 and 10? Of course there is. Half of you are saying, yeah, I knew there's 0 numbers between 9 and 10. But that's yes and no. There's 0 whole numbers between 9 and 10. But there are a ton of measurable quantities between 9 and 10. How many? All right, well, let's talk about them. We have 9.5, right? 9.3, 9.32, 9.4. Just keep going and keep going and keep going. So how many quantities or how many different measurements can you take between 9 and 10? If you had a number line in front of you, remember the number line when you were a kid? Put your finger on 9, put your finger on 10. Now I want you to move your finger between 9 and 10, and I want you to tell me how many different places you can move your finger. That's a trick question because the answer to that question is actually been baffling mathematicians for a long time because, let me put it to you in a different way. Let's just say you're at 9, and then I want you to take your finger on your number line and move it between 9 to 10. So you move it halfway. Cool. Duh. Got it, Bob. Not stupid. And then I'm like, all right, now I want you to move your finger from 9.5 halfway to 10. And you move it again. So now it's like 9.75, right? Duh. Now I say move it halfway to 10 again. Now you keep moving it. So you're constantly moving your finger, right? Now take what I just said and multiply that by 1,000,000. All right, 1,000,000 times I want you to move your finger towards 10. Each time you move your finger, you're observing a quantity, right? It's a different decimal. It's 9.9, 9.999, 9.99995, 9. Blah, 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 all the way through whatever. Okay? You got it. So that's actually a conundrum, not a conundrum. That's actually a problem we're going to explore later in the semester. But for the fact of what I'm doing here, I'm getting off on a little bit of a tangent, but I tend to do that. That there's an infinite number of observable quantities between 9 and 10. Okay? You get the decimals, right? 9.5, 9.3, decimals. Fractions. You guys learn fractions, right, in third grade. Okay? Fractions, and when we talk about decimals like that, we're not talking about integral numbers. We're talking about real numbers. A real number is pi, 3.14. It is I don't know, think about anything that's got a decimal in it. Well, I'll leave you guys to figure it out. But I mean, there's some things that are a little bit different, like for example, or could fall in each category. So don't really get too hung up on this. Like when people ask you your age, you usually give it to them in a whole number, right? Unless you're a little kid. Someone will say, "How old are you, Bob?" I'm like, "I'm 29." And then they laugh. And they're like, "Yeah, right. We've seen you. You're not 29." But anyway, you describe that in integral terms or whole numbers. When you're a kid, you'll say, "I'm 8.5" or "I'm 9.5." But after a while, when you ask a grown-ass adult how old they are, they say, "I'm 21 years old." They don't say 21.5. But what I'm trying to say, though, is some things we're used to expressing in real numbers, such as your tax percentage might be 0.285634, or your raise percentage might be 0.1. If you're getting a 2% raise, or 2.5, 0.025, or something like that, or the I don't know. Or if you're cooking, you put in a cup and a half or something like that. And some things are expressed. Well, I just mentioned real numbers. Some things are expressed in real numbers, and some quantities are expressed in whole numbers. Now, discrete math, again, what we're doing is really dealing with the whole numbers. There's a little wiggle room in there, but we're talking about different ways that we look at numbers. Now, let me go on with this. We talked about a little bit about whole numbers versus real numbers. Let's talk about some other numbers. Again, you're sitting on the red line with me, and we're going by Wrigley Field, and, I say, look outside, I want you to count the cars. So you count the cars. You're like, I see 75 cars. Okay, good. And then I say, I want you to count the number of people on our car, and you say there's 50 or whatever. Notice that when you observe something, you're counting. You're basically, what you're doing is you're getting a quantity, right? Your quantity are the things that you're counting. Let me ask you this. How many things of 0 do you see? That really raises an interesting problem, doesn't it? Because I can count the people on the train. I can count the things in my backpack. I can count the buildings outside, right? They're all positive numbers, aren't they? Aren't they? They're all positive. How many of 0 things do you see? You scratch your head. That's really an unsolvable problem. So, you're like, well, 0 of what? I'm like, 0 of anything. And you would say, well, I see infinity of 0. I see 0 elephants. I see 0. I'm trying to think of things that you wouldn't see. I see 0 statues of liberty. I see 0 fish, okay, because you're above ground. I see 0, and you just go on and on. You're just like, well, how many 0 things do you want me to mention? And I would say, well, for the sake of argument, I want you to mention everything of 0 that you see. And then you just would mention there, you'd say, well, I can't answer that because I see 0. Basically, 0 is the absence of a quantity. It's the absence of anything that I can observe. And then I would say, exactly. That's exactly what 0 is. 0 isn't even a number. 0 is the absence of a number. It's the absence of a quantity. Again, that's going to become very important to us a little bit later. Also, I want you to take a look around you. I want you to tell me, how many negative things do you see? How many negative, I'm just going to mention things around me. How many negative headphones do you see me? How many negative fish? How many negative microphones do you see? And then you would say, I don't answer the question. As well, how many negative? Do you see negative 1 bananas around you? Do you see negative 2? And you'd say, I can't see negative things. All right, I have to imagine that. And I would say, correct. Anything that's a negative, we call an imaginary number. And that's going to become important to us too. All right, so when we talk about discrete math, I'm kind of circling around here. It's about us understanding all these little things. Rather than me starting to throw all this crap at you and drawing on the board and say, we're going to do this, that, and the other things, I need to start here. I need to kind of poke your inner mathematician that was so full of wanting to learn when you're in first and second grade that we get your scrolls destroyed for you. Not your teachers. I'm just saying that somewhere along the line we lost our way in trying to understand this stuff. And then we started fearing it and then thinking that we had to do it just because we said we had to do it. But the answer is we really do need to do this. And hopefully by the end of the course that you'll, or at least my course here, you'll think the same way. So, all right, let me sum at least that up. Okay, so we talked about whole numbers. We talked about real numbers. We talked about quantities. We talked about observations. We talked about the conundrum of zero. We also talked a little bit about the absence of quantities and the negative are a different numbering system that we call imaginary numbers. Now, more on all of this as we go, right? Remember, this is just getting us started. So let's go on a little bit. Now let's talk about how we use these numbers, right? Now we use numbers to do really 2 different things. We use them to describe things. Now think about the this is a good one. Remember, just a few minutes ago, I was giving you an example on how in our early civilization, we didn't teach ourselves math because math was already there. We started understanding it and we started putting it together, right? We did. So let's talk about what we did. Let's just say, for example, that we would do things such as when we would go out and hunt, right? And we would notice that it would take, how about this? When we would bring out, let's not do hunting. Let's do something a little bit more gentle. We're gathering fruits and vegetables and berries and all this other stuff. So we send out a party of 10 people to go do hunting and go do some gathering. My wife is a vegan vegetarian, so we'll stay away from hunting. Okay, fair enough. So we measure it. When we send out 10 people, we come back with 100 pounds worth of stuff, right? And we notice that if we send 5 people out, we bring back 50 pounds worth of stuff, right? I'll say this slowly. And if we send out 200 people, we bring home 200 pounds worth of stuff. See a trend there? We did this early on, and we started doing what? We started taking our observations, right? 10 gatherers bring back 100 pounds. 5 gatherers bring back 50 pounds. 20 gatherers bring back 200 pounds. Believe it or not, really early in our development, that was new to us. And we're like, hey, we see a pattern here that the more people we send out, the more of this good stuff we get to eat, right? So we started measuring that. And we said every time that we send people out, we're going to measure how many people went out, and we're going to measure how much of the good stuff that they brought back that we could, eat by our campfire. So after we did that dozens and hundreds of times, all of a sudden we had a bunch of observations. Now, believe it or not, that was an early database. That's data right now, is we have these observations that we recorded that we could go back to, right? So that was a big step in our evolution when we learned how to do that. It might sound silly now, but that was new to us way, way, way back when. But from there, we got smart people, hopefully smarter than me, that would look at all this data and say, you know what, for the past 2 generations, for the past, 50 years, I don't know, how long is a generation? Work with me on this. For the past 50 years, we've been writing all this down, right? We were writing all this down, and we're noticing trends. We're noticing that when 10 people used to go out, they used to bring back 100 pounds, and then slowly over time, it got to 90, then 80, then 70. Now when we send out 100 people, they're only bringing back 50 pounds. So we look at that and we start to notice patterns. Now that's important too, because when we discover patterns, we really change the way we think and we go into the other thing we do with math. That was the first thing we do with math. The first thing we do is we use math to describe things. And that's what we did there. In my example, we were describing something. Then we can use those descriptions and we could do the second thing that we do with math is predict. Now this is important and this is something that's all the buzz now. You hear this predictive analytics, big data, we're going to go and we're going to run informatic predictive reports. What does that mean? That just means that we're going back and we're looking at the things that we described and we're going to make predictions. It's simple. For example, we'll go through another example. Let's just say we're gonna describe something. We're gonna describe how long it takes Bob to get to his classroom. Bob's always late, by the way. So as you guys know, because it's taken me a day longer to post these lectures than it should. So let's go over this. Let's just say it takes Bob 30 minutes to get to school. And then on day 2, it takes Bob 31 minutes to get to school. And then on day 3, it takes Bob 29 minutes to get to school, right? Don't write this down. Just listen to me. We're okay. We're among friends here, okay? Next time Bob goes to school, it takes me 33 minutes, right? Okay, I'm not going to lay anything heavy on you. For the next day, I would ask you, predict how long it would take Bob to get to school. What's the first thing you would do? The first thing you would do, right, you would look at your observations. That's exactly what you should do. And you know what? I didn't have to tell you to do that. You knew how to do that. You knew, let me just look at the data. Let's look at what the prior observations were. Let's look at how we described it. You already did that. And guess what? I didn't teach you how to do that. You already knew how to do that. And you would say, okay, 29 minutes, 30 minutes, 31, and whatever I said. And then you would say, all right, I'm going to take a guess. Good. A guess is called something. It's called a prediction. Okay? And guess what? I didn't teach you how to do that. You already knew how to do that. And you would say, I'll guess 31 minutes. Okay? That's called a prediction. Now, if you knew the math behind that, you could probably make a better prediction, okay, and say, you know what, I need more data, okay, because you would say there's only 4 days, I need more, okay, and you're right, okay, you need more samples, you need a bigger sample size. Guess what? I didn't teach you how to do that. You already knew that your sample size was small. So let's just say you had a sample size of 100 days, and you look at it, eventually you would notice patterns in the numbers, and then you would say, you know what, I guess 31 minutes. Okay, that is important because you made a prediction. Now, what we're going to do is in this class, I'm going to show you the math behind that, how to make predictions like that. And also, I might ask you a question. I might say, 31 minutes, huh? Are you sure? And then you'd say, well, I'm pretty sure. Okay, well, that's another mathematical concept called confidence. So we're going to be doing all this stuff. But the thing is you already know how to do this. I just need to show you the steps and how to take your logical mathematical mind and just apply it and actually do these things. And you're going to find out that it's fairly simple and straightforward as long as you know the context of what you're trying to do. So those are the 2 things that we use math for. So let me kind of in my head review what we did so far. We went over a little bit how I approach the class, what my goals are for you. We went over why you're afraid of math and how we're trying to change that. I'm trying to change that, hopefully with you. We went over basics of different numbering systems, real basics of it. Then we went over what math is for, again, for prediction, to describe things and predict things. I think that's all I wanted to do today. That's kind of a lot. I do got one more thing. I'm going to talk the difference between like a theorem and a proof without going into like a doctoral thesis on this. It's simple. It really is simple. You could probably describe to me or to anybody what a proof is in a theorem in about 10 seconds. Although, if you Googled it, a lot of papers make it sound more complicated than it is. See, that's one thing I want to... Let me get on a high horse for a second, and then I promise I won't. Maybe I will again. Is mathematicians, we like to make ourselves look cool. You know, that we're going to make it harder. And if you don't understand this, obviously, if you take a look at blah, blah, you know what? Screw this. Don't make it harder than it is. And I think we just do. You know, this stuff isn't hard. And we make it harder than it is. So one of the things that you're up against is when you do a lot of this reading, a lot of it is like, and that's why, like in the reading I try to give you the real simple stuff. Don't think it's dumbed down. It's not. It really isn't, because this stuff is not hard to understand, and sometimes the more complicated it looks, it's unnecessary. It's really, really unnecessary. So don't think that some of the stuff that I give you is dumbed down. If it is, I'll let you know. If it is, I'll say this is a very simple way, but it describes it really well. But anyway, let's talk about a little bit between a proof and a theorem, and then I'll let you go and give you, the rest of your life back. At least your life out of here. Now, remember we talked about the example of, early civilization when we would send gatherers out to go get a bunch of berries and nuts and things like that. Okay. So we would send out 10 people and they would come back with 100 pounds worth of food. And then we would send out 20 people and they would come back with 200 pounds worth of food. And then we would send out 30 people and they would come back with how many? All of you are going, 300, Bob. I know this one is 300. Okay, what you just did is you just did a proof and a theorem in your head. That's what you did. The theorem is looking at what your past math and I'm being overly simplistic here, but just bear with me. I'm giving you the gist of it, okay? Your theorem is looking at your past mathematical observations and making a prediction. Okay, so if 10 people bring back 100, 20 people bring back 200, 30 people will bring back 300. Now, again, I realize there's variability in there. It might rain, it might slip, maybe one of the gatherers was sick that day, but just bear with me on this. Let's work. Let's put on our imaginary common sense hat. Let's just kind of work with this a little bit. So that would be an actual theorem. Your theorem would be to look at your past events and come up with what your theorem is going to be. Now, you can prove that. Okay, like for example, I'll give you another example. Let's just say, and this is a good one. A proof is something that you can prove mathematically, but you might not necessarily. Well, you prove mathematically, but underscore or sub. Point here, you might not be able to really prove it mathematically. This is an example. How about this? It takes me, there's a 7-Eleven across the street from me. The 7-Eleven is 100 feet away. So if I walk 100 feet to that 7-Eleven, it takes me 5 minutes, right? I measure it. It takes me 5. It's something that's measurable. I measured it, okay? That goes with my theorem. Then I go 100 more feet, which is where I parked my car. Then I go and then I measure it. Then I go 100 more feet and I measure it. So I say, let's do this again. So in 100 feet, it takes me 30 seconds, and to walk 200 feet, it takes me 60 seconds, And to walk 300 feet, it takes me, I measure this. Remember, this isn't a theorem. I'm measuring it. It takes me 90 seconds. Okay, 30, 60, 90, 100, 200, and 300. Okay. Now, I can ask you, right? I'm like, well, how long would it take me to walk 5 million feet? Now you're laughing, you're like, aha, Bob just picked that number out of his head. No, how long would it take me to walk 5 million feet? Now, immediately a couple things. Again, I'm trying to explain this in non-mathematical terms. First of all, you'd say, well, can you really walk at 5 million feet? And the answer to that question would be, well, no, and I'm not going to. I'm not going to walk 5 million feet. I'm not going to measure it. I'm not going to do it. All right, I don't know how long 5 million feet is, but it's certainly something I'm not going to do. But, I could, as a theorem, you would be able to take the 100, 200, 300 based on those observations, right? And you would be able to give me a theorem of a theorem of how many feet I would walk, or how long it would take me to walk 5 million feet. You could prove it too. You could prove it by using the math. You could basically go and look at the prior results, and you could prove it. You could say, well, if this is how long it takes for, again, let's eliminate variability. Let's just say I walk exactly at the same pace. Okay, just to keep it simple. You can look at the math and determine exactly what your proof is, and you could prove it. You can mathematically prove it. And what's important is you can mathematically prove something that might not be able to be observable. And that's important. That's really important, because when we deal with math, often when we do proofs, we have to prove something that we can't measure. Like, that's actually a good example, because I don't think I'll ever walk like 5 million feet. Or how about this? This is another one. Let's just say I go to that 7-Eleven and I don't smoke. I don't smoke, but let's say I go to the 7-Eleven and I buy a pack of cigarettes for $20. That's how much they are in the city of Chicago. Okay, pack of cigarettes, $20. Then while I'm at the 7-Eleven, I'm like, you know what? I need 2 packs of cigarettes. And then I observe that it cost me $40. Then I buy 3 packs of cigarettes. Now it's $60. Okay, right? So my question would be, how much would 1 million packs of cigarettes cost? Immediately you would say, well, you can't observe that, because the guy at 7-Eleven doesn't have 1 million packs of cigarettes. So you can't actually mathematically go through it and actually do it. That's important, because that's where theorems and proofs come in. Because you have to start making, and I'm trying to use non-math terms because I don't want to scare you off. You have to guess, right? How much you would have to guess how much 1 million packs of cigarettes cost. But all of you would say, wait, Bob, I don't got to guess on how much 1 million packs of cigarettes cost, because they're $20 a piece, right? And I'm like, yeah. And you say, well, yeah, I'll just take 20, divided into 1 million, or pardon me, sorry, it's getting late. I'll just take 1 million and I'll multiply it by 20, and I'll get my answer. That's how much, 1 million packs of cigarettes would cost. And I would say, is that a theorem or a proof? And you would say, well, it's kind of a little of both. I mean, I can prove it by taking your observations and saying every time you bought a pack of cigarettes, it's $20. So 1 million of them will cost you $20 million. Okay, now but that's what our proof is. That's something that's really not observable, is it? That's important in math, and it's going to be important in discrete math, especially when we talk about theorems and proofs, because sometimes we have to prove something mathematically that we just can't duplicate. You could say, well, you know what? Has anyone ever went to that 7-Eleven and bought? Has anyone ever went to that 7-Eleven and bought 1 million packs of cigarettes? No one has. But if they would, it would cost them $20 million. And that would be indisputable. You would say that's mathematically plausible. Again, I'm trying to use non-math terms for you. All right, that's all I had for you for today. So thank you for listening. Thank you for making it this far. And if you have any questions, please reach out to me. You know where to find me. So be safe, and I bid you all a very well rest of the day. Thank you.